All right, today we are dealing with ordinary least squares, which is also a build-up from our first topic. A build-up from our first topic. So, if you are still having trouble with what we discussed on the first topic, I think the notes that we provided last week are very quite detailed. Right, they are quite detailed with that. Right, so estimating. So we are dealing now with ordinary least squares. Okay, estimating a single independent variable model, estimating single independent variable models, all as ordinary least squares. So every time we talk of OLS, it's ordinary least squares, which is one of the methods that we use in going about our estimations here. So the purpose of regression analysis is to take a purely theoretical equation. This is in theory where you find the stochastic error, right? You find stochastic error there, and then we want to create a set, to use a set of data to create an estimated equation in that format there. So which is what we discussed again in the previous session when we were saying once you see these beta heads, right? Once you start seeing these beta heads there, know that we are dealing with estimates, right? We are already dealing with estimates at that point. So which means we already do have a set of data, and then we are using that set of data to basically come up with estimates. So those estimates you use to draft an equation like this, right? So this y here is supposed to be y1, right? Sorry about that cap there. Cap is gonna fall on those beta coefficients there, right? And remember what we said again the last time. We said these are supposedly estimates of the true values. So these are the true values which we said in terms of the true line, it cannot be observed because it's a representative of the population, right? And of which you can't really get data of the population, right? And then come up with a line like this. There are a lot of reasons why you can't get that information. So the best that you can do is to get a sample of data and then hoping that that sample is representing the population enough for you these estimates that are very close to your true values there. So these are population parameters, right? Population parameters, and then these are sample parameters, right? So you use, it's like a situation where suppose it's a youth school, right? And you want to draw certain conclusions about the youth school, but for some reason you can't test everyone in the youth school, but you can basically say out of 500 students, you probably get a sample of 300 students, right? And then you are hoping whatever you there in terms of what you can students is gonna be representative of those 500 students. Say you have a product that you want to sell kids within a certain age group, right? You can obviously ask everyone or every kid in the country that's within that age group, but you basically get them, right? Get a sample and then you ask those kids around, you just ask those kids, are you guys willing to consume a product like this? And how much would you be willing to pay for something like this? You basically get information about that. So whatever information you get there is going to be your sample parameters for argument's sake in terms of this equation here. That's going to be representative of your sample parameters, which you can therefore use to make estimates about the true population. Right? Okay, so if most of these kids uh, respond in a certain way, then we can assume that the rest of population is going to in that same way. So this is basically what happens. So in coming up with this now, the most widely used method in obtaining these estimates is your ordinary least squares. So now that you have your sample, right, how then do you come up with parameters? Right? How then do you come up with these coefficients and the most OLS, which your is. But why is that the case? Right. Although your OLS is the most regression estimate, it's not the only one, right? I think we are gonna see actually a couple of others, including your general least squares, but this is the one that we normally use, right? Why? Number one, it's very easy to use. Number two, the goal of minimizing this here is your residual, right? So this is your sum of residual squared. That's your sum of residual squared. Is quite appropriate from a theoretical point of view. So the thing is, your OLS basically limits or reduces or minimizes rather, the sum of squares, right? Your sum of squares in terms of your residuals. So which is why in any case we call it the ordinary least squares. So least is the smallest, so it basically limits that. And I'm gonna explain why that has to be the case. So remember, this E here represents your residuals, and we already said by definition, your residuals there represent your deviation of deviation or the distance between your estimated line, right, or the points that lie on the estimated line, and then the actual observation. So if we are saying you want that minimized, you are basically saying because your estimated line should be your line of best fit, right? So if that distance is minimized between all those points, in other words, it's the smallest gap that you can find between those points. So we are basically saying your ordinary least squares gives you the equation of the line that's going to be best fitted on that graph, because you are saying you want a line of best fit, so it must cut across somewhere in the middle there. And then of which the middle is the point where all those residuals are minimized. So in other words, you're saying all the points basically need to be catered for as much as possible, right? So hence, you prefer a line to minimize your residuals as possible, just for them to be as small as possible. So the theoretical point of view here is your line that best represents your data. So your data is a scatter plot, basically. So a line that's going to best represent your data then will basically be a line that cuts somewhere in the middle, right? And then if the line cuts somewhere in the middle, then we are basically saying your residual squares, they need to be minimized. And I think it's explained much later there why we are squaring this. If it's not explained, I'm gonna do it before the end of the session. Right, number 3, your OLS estimates a number of useful characteristics. So these two are the biggest. The sum of residuals is exactly 0. Right. Why is that the case again? This line basically runs in the middle of your data on that scatter plot, basically runs in the middle. So which means your line that gives you this equation here, right, that gives you this equation, which comes from using your ordinary least squares. We're basically saying the sum of residuals is going to be 0, so it runs in the middle. So all the residuals above are going to be equal to all the residuals below, right? So in other words, the data that lies above must be the same as the data that lies below. So which is same in terms of additive value, right? Not exactly that the data has to be the same, but in terms of addition, if you sum it up all together, it must be 0, right? That's what we basically mean. So it basically lets us know that our line of best fit runs in the middle of that scatter plot. And then again, the OLS can be shown to be the best estimator, right? Possible under a specific assumption. So we are gonna deal with that on the next, maybe next session or 2 sessions from now, right? Here is the assignment question now. An estimator is a mathematical technique that is applied to a sample of data to produce a real-world numerical estimate of the true population regression coefficient or other parameters, right? Thus, the OLS is an estimator, and beta heads produced by OLS is an estimate. So I think the assignment question there has been, so we use the ordinary least squares as our estimator to estimate what this beta head coefficient there. Right. Basically, there are many other estimators that we can use, but with what we are dealing with here, our OLS is the best estimator. And then we are estimating our beta coefficients. To estimate, you basically give it a value of what the true population could be. That's what we are, or the true population parameter could be. All right, using your ordinary least squares. So select the estimate of beta nil and beta 1 that minimize the squared residual summed over all sample data points. So basically what we are talking about, they want to minimize. So in minimizing, we are basically trying to come up with the best estimate, the best line that can represent all the data that we expected. All right, then these are the formulas. I think these ones we are familiar with from statistics. So we're not using these on the test assignment because we're simply running that on Excel. But this you can basically do. I think typically in an exam question, you could get this there. But how you get this, you normally wouldn't have to calculate your summations here. You normally wouldn't have to calculate your summations. I think most of this data would be given. So your xi minus your x bar is normally going to be given as your x there, your small x. So that basically gives you, so I, every time you see this little I, it represents the points that you are given, or that from your sample, your x values from the sample. That's what. So this one basically shows you that it could be x1, x2, x3, x4, right? Depending on the number of n for the sample. Maybe if you've got 50 as your sample number, it will simply get up to 50 there, right? And up until 50. And then you have the mean or average, right? Which you can easily calculate, but you are most likely going to be given that there. The same with your y again, you're basically getting your y from sample. This is bar. So yi minus y bar is normally going to be given as your y. So sometimes this is going to be written as summation of xy. So you are basically summing up your x times y. So your x being the difference between that there, your y being the difference between that there. So you can see basically that this will give you a deviation between, because the points that lie on your x bar anyway are normally going to be the points that cut in the middle of your line, right? And then same as y there. So it should be very interesting theory behind this, but it's good that we don't cover that here, right? Maybe if you are studying statistics, you might want to find that out. All right, and then again, you're gonna have your summation of x squared here, which is basically this here squared, right? So you are squaring this with every value, and then you are adding that together. But again, like I'm saying, for our exam questions, we are basically going to be given these and a lot of other things. So you basically need to know which ones to pick there. So very easy, you can simply have the formula, but it's an easy formula anyway to pick up, right? So what does this give you? It basically gives you the gradient of the line. So remember, when you're dealing with a simple regression line, this is going to be your first beta coefficient, right? Your first in terms of beta 1, but your constant, this is how you get your constant here, right? Very easy, but you can simply just know the formula here, but it's basically derived from y plus c, or c plus m. This instance, this is your gradient, and then here you've selected your x bar being your point there, and then there your y bar being your other y value there, because definitely your line is going to be crossing those two values there. Then you use that to find the constant. And again, most likely this you're going to be given, and that you're going to be given. And this you will have calculated.
Hi, Ntando, we can't hear you.
I say.
About that.
Say.
I was kicked out. All right. So I was still saying, if you look at your E squared here, now we already defined our residuals earlier, and we're saying these points here, the points that lie on your right, it's basically the difference between the points that lie on your graph, right? So which are the points that lie on your estimated, which is that one, and then again against the points that you've collected from your data sample, which is your yi there. So it's basically the difference between your estimated line and then what you get from the data. Because remember, we say those points don't exactly lie on that graph that you're going to come up with, on that line, based on the equation that you're going to come up with, because it's a scatter plot, right? So the difference between that is your residuals. So we basically want to square that, so that, and then the OLS is going to give us the smallest difference, so which is the least amount of your squares there. That's what you get from your OLS. So in other words, if you use other estimators with the same data, so another estimator could be just maybe guessing a line of best fit, for example. You just put up a line there, and then sometimes I think when we're doing this some years back in mathematics, we'll just join two points there. You basically just join 2 points. You are basically using your mind or using your eye to see where your line can fit in there in the middle. So suppose you just guess your line and you put up a line that can join one of those, or sorry, 2 of those points on the scatter plot, and then you can come up with an equation. So once you do your residuals, you calculate your residuals there. That's the smallest value of your residual squared. It's not gonna give you that. So this here can basically be expressed in this manner, right? Can basically be expressed in this. So this one here, your beta naught and your beta 1, remember, these are representative now of the equation of that line, right? So it's usually gonna be a beta naught plus beta 1 heads xi, right? So it has become negative here because we are subtracting that, right? So you just want the smallest value for that. That's what this is all about. So that was simple model. So from then on, we can jump to a multivariate regression, so of which we already defined on the previous session, and we're saying now you don't just have independent variable, so you have multiple independent variables there. So you can then have an equation that's got number 1, x variable number 2, up until God knows how many you're gonna have there. So the difference now with those two comes with your interpretation, right? Let's talk about the interpretation, which we already mentioned in the previous video, right? The biggest difference between the interpretation of the slope coefficients. You interpret the slope coefficients here. So the change in the variable associated with 1 unit increase in the independent variable question. So holding the other independent variables in the equation. So we are constant other independent variable. So this one, and then you are basically holding these up. So we are assuming that these ones don't change, right? So we are talking about a change in one variable. Think of, I think last week again I gave an example. Say if you look at demand, right? A person's demand for a product can be influenced, say, let's say by income, can again be influenced by price of the product, can also influenced by the price of other related products, right? So if you're gonna be interpreting, now we've got 3 independent variables, or 3 independent, sorry, 3 influencers, right, there in terms of things that can influence a person's demand. So if you're going to be interpreting each and every one of them and you have an equation like this, then you should not fail to mention that you are holding the other ones constant. So this is what you expect to change. Suppose the things that you expect on your Y, which is going to be a person's demand of a commodity. When, say, the price changes, assuming that a person's income doesn't change, and also that the prices of related commodities don't change. So once you miss it there, then you are basically making multiple changes, and you can't use that decisions, right? Because you want to make this information that you get here useful, right? So hence, going to be isolating these coefficients and seeing the influence that each and every one of them has on the y variable. Right. So all of O your betas that minimize the sum squares of residuals always, right? So this is how you calculate this one now, right? This is basically how you calculate this one. So this again, in an exam situation, you are going to be given these values. So you are just going to be substituting these values there. So which means, I believe on the list of formulas, you might have this there on the question paper. You might have this on the list of formulas. So it's just it's just your application of this. But in general, if you're going to be doing this for a living, then you can easily run this up like we did on Excel, which will just give you those values straight up. So it's not complicated there, right? And then much related to the assignment that we have, again, we need to know what our total, explained, and residual sum of squares are. So if you realize, or if you remember, when we ran that on the Excel spreadsheet, our solutions gave us the total sum of squares, the explained sum of squares, as well as the residual sum of squares. Right, so we need to know what these are. All right, so our concepts commonly used in the context of statistical analysis, particularly in the context of regression analysis, what you are doing. So these terms are used to partition the variation in dependent variable. So a variation, of course, in dependent variable, we're talking about your change in y. So which is the variable that we are trying to predict or trying to explain. Ever change into different components as goodness fit of the regression model. So this is what we are talking about. So in terms of goodness fit, I think I do have it earlier. They will try and mix up the two and see. So this is basically what's in the assignment. It's like I knew that they were going to ask us this. So total sum of squares represents the total variation in the dependent variable, which is y. So to put it plain, your TSS, which is your total sum of squares, is equal to your ESS, which is your explained sum of squares, and then plus your residual sum of squares, which is going to be this one here. Sorry, the last one there, your residual sum of squares. So if you add up those two, it's going to basically give you your total sum of squares. So this is what you get. Your total sum of squares is that, right? Which is all your variations between your expected, right? So in other words, between your this is your y bar, your average there, and then against the points that you are getting. So the total of those variations is your total sum of squares. So in other words, any change in y, that's what we are talking about there. And then your explained sum of squares. So this is also known as your regression sum of squares or your model sum of squares. So it represents the variations in the dependent variable that are explained by the regression model. So by that, what do we mean? Your explained sum of squares is your variations in your y and the that independent. Remember, the independent results and this can explain sum of is we are talking your y is changing, and assuming changing by would be expected within x, right? So those that can be explained are therefore put up under your ESS. But remember, last session we were saying there are some of the changes that cannot be explained by your variations in x, right? Suppose there's an instance where your x didn't change for some reason. Okay, I think I'm having on the other gadget. Just re-put that there. Right. There could be an instance where there is a change in your y variable which cannot be explained by your x variable. So that there is going to be catered for under your residual sum of squares. So which is the one that represents the unexplained or the residual variation in the dependent variable after accounting for all the variations that can be explained by right. So related sum of the differences in of data points and the predicted values from the regression. So mathematically treated as follows. So every time you're explaining this, always make sure that you need to put up your equations there, right? So that's your residual. So it's linked now to evaluating the quality of the regression line. Okay, this I'm gonna do last. So let me just jump to where we can directly link this. So is where
Ase. I can hear you
sorry about
clearly.
that.
Yes, yes. I can hear you.
Yes. So I was actually out. I had actually been cut off, so I'm only back now. But we are finished up. We are just on the last one now. All right. So in terms of the speed of the regression, right? So we are talking about how well our data fits into our model. Right? So your R squared often simply referred to right, as R squared, and how well dependent variables, our predictors in a regression model, explain the variability in the dependent variable. So the range is usually 0 to 1. Right? Can you guys screen there? What I'm sharing on the screen? Is that one still there?
Yes.
Yes.
All right, perfect. So the range is usually 0 to 1. So it represents the proportion of the total variation in the dependent variation that can be explained by the independent variable. So now that you know what your RSS and your TSS is, you can basically see what this is. So if your total of these has to be 1 at the end of the day, and then your R squared is 1 minus your RSS divided by TSS. So looking at this mathematically, because we are dealing with the total variations that can be explained in proportion of total. So yes, the variations that can be explained in proportion of total variations, then this can simply be written as your ESS divided by TSS. It will basically give you your R squared. Right. And then Now we have a modification of that R squared, which takes into account the number of independent variables in the model. Right? The reason why we have an adjusted R squared is because we realize that if R is going up, it's basically saying that your data is a better fit, right? Now it means it's growing. So basically saying your variations in Y, right, according to your model. But we realize that this one simply by adding an exponential variable, this one goes up. So to prevent that from happening, then we need to adjust that then for the number of independent variables, which we say these are degrees of freedom. So you just make an adjustment there on your R squared for your degrees of freedom. Then from there, you will see whether it's a perfect fit or not. So adjusted R squared penalizes the inclusion of unnecessary factors by adjusting your R squared based on competitors and the sample size. So by penalizing that, we are basically saying we are preventing that from going up for no reason, right? We are basically preventing that from increasing for. So that's why so this is gonna be basically 1 minus your 1 minus R squared, and then you're multiplying n that by n minus 1, and then you're dividing that there by. Right. I think the one that's in the textbook is not clear there. We're going to use that. All right, and then here I'm going to need you to read that one, the misuse of, okay, it's supposed to read just the misuse of the adjusted R squared, which are the circumstances where you might find yourself misusing the. So ideally, you want to have a high R squared, right, because it shows that your data is a perfect fit now. But just read through the circumstances where that becomes inappropriate. All right, so we're going to end with evaluating the quality regression. At the point, you have come up with your equation. So we'll be building on from this on the next session. At this point now, then you've used that sample to come up with a regression equation. Now, how do you evaluate the quality of your regression model? So below is the list of questions that you should ask yourself when you're evaluating. Right? Is the equation supported by sound theory? We've spoken in depth about this. Right? How well does the estimated regression fit in the data? This is our R squared that we were talking about. Is the data set reasonably large and accurate? So you can't draw a conclusion using a data set while you want to draw a conclusion about 1,000 people. It must be reasonably large. Right? Is OLS the best estimator to be used in this equation? Sometimes it's not the best estimate. And then how well do the estimated coefficients correspond to the expectations developed by the researcher before the data set was collected? For instance, here you have your expectations, right? Usually being different, so you know how different variables behave with each other. So now you are basically saying, are those coefficients, or do those coefficients in terms of values of those coefficients as well as the signs attached to those coefficients fit into expectations there? And then are all of the important variables included? So in other words, if you want to explain demand, you want to try and include everything that affects demand. So that's what we are basically assessing there.